Back in Chapter 2, when deriving transfer functions from models for physical processes, we considered two tanks in series that both had gravity-driven flow out of the tank, such that the first tank drained into the second tank, but the behavior of the first tank was decoupled from the behavior of the second tank based on the configuration. A much more realistic configuration has the two tanks sitting at the same ground level. In this configuration, the height of the fluid in the second tank can influence the behavior of the first tank, because the gravity-driven flow across the resistance out of the first tank is proportional to the difference in the fluid height between tanks 1 and 2. Therefore, the behavior of the first tank is coupled to the height of the fluid in the second tank. Now, our original configuration gave rise to a second-order transfer function relating perturbations in Q2, the effluent from the second tank, to perturbations in Qi, the input to the system. If instead the flow rate Q1 is related to both H1 and H2, how will these two tanks behave? Well, let's rewrite our model. Here, recall A1 and A2 are the cross-sectional areas of the tanks, and R1 and R2 represent the resistances to the gravity-driven flow, either between the two tanks for R1 or out of the second tank for R2. The accumulation of fluid in the first tank is equal to the volume flow rate in minus the volume flow rate out, which is related to both H1 and H2 in our new configuration. The accumulation of fluid in the second tank is also related to the flow between the two tanks and the flow rate out of the second tank. Again, I want to point out here that the difference between this and our original two-tank model is that now the model for the first tank contains the height for the second tank, so these are more highly coupled. When we take the Laplace transform of this new model, we find that H1 is related to both Qi and H2, and of course H2 is related to H1. We can use this second equation to eliminate H2 from the model for the first tank. Now, to find how the inlet flow rate affects the height in the first tank and derive the transfer function H1 prime over Qi prime, we need to bring these other H1 terms over to the left-hand side of the equal sign. Then we can find the ratio of perturbations in H1 to perturbations in Qi. Now we have a first-order polynomial in S in the numerator of a second-order transfer function. And this second-order transfer function only describes the behavior of the first tank. But because the first tank is coupled to the second tank, we see that our tau A term contains the area and resistance for the flow out of the second tank. And the tau and zeta terms in the denominator of this transfer function also depend upon the features of the second tank. You can show that for meaningful values of R1, R2, A1, and A2, that this second-order transfer function is overdamped. That is, zeta should be greater than 1. Remember that in our original model, the relationship between H1 and Qi was a first-order transfer function. Now we have a much more complicated second-order transfer function with numerator dynamics. Let's generalize the behavior of this second-order transfer function with a first-order polynomial in S in the numerator and find out how these systems behave with respect to step input changes. This is actually entry 23 in table 3.1. So using table 3.1, we can immediately write the time domain response. The step input to this transfer function results in an expression that has 3 poles and 1 zero. Just like for the step input to the lead lag element, we have a pole at the origin, which will give rise to a non-zero steady state gain in the time domain. Now we have 2 negative real poles that will give the sum of 2 exponentials in the time domain, with magnitudes determined by the 0 at minus 1 over tau A. Just like for the lead lag element, we can classify different types of behavior. This is plotted for tau 1 equals 4 and tau 2 equals 1, with various values of tau A. And we see behavior similar to that for the lead lag element. That is, when tau A is greater than both of the denominator time constants, tau 1 and tau 2, we have overshoot, where the initial response to the step input goes past the final steady state and then decays to the final steady state. And when tau A is less than 0, we have a 0 in the right half of the complex plane, which gives rise to an inverse response, where the initial response to the step input goes in the opposite direction of the final steady state before decaying to the final steady state. Notice that because we're not changing tau 1 and tau 2, all of these have the same kinetics of the response to the final steady state. They all approach the final steady state in about the same amount of time because the denominator time constants, tau 1 and tau 2, determine the rates of these exponential decays. But by changing tau a, we change the initial direction of the response. When tau a is greater than 0, but not larger than both of the denominator time constants, then the system expresses neither overshoot nor an inverse response. The behavior of this system seems to oscillate, but these are not really sinusoidal oscillations. These are just the sum of multiple exponentials. Remember that this second order system we said would be overdamped. So this behavior where the response to a step input changes direction, either because of the overshoot or the inverse response, is due to the numerator dynamics, not due to complex roots of the denominator polynomial, which would give rise to sine and cosine functions. These are simply the sum of exponentials that decay in opposite directions with different rates. Notice also that the characteristics of overshoot and the inverse response have nothing to do with the magnitude of the step input. They only have to do with the relative values of the taus in the transfer function. So that means that if the transfer function exhibits overshoot, a step input of any magnitude will cause overshoot, even a very small input. Or if the transfer function exhibits an inverse response, the response to any step input will have an inverse response, regardless of its magnitude or its sign. We derived this transfer function for two coupled processes that occur in series. That is, the two tanks were in series. The same type of behavior can also arise for two first-order processes that are in parallel. If the same input is fed to two different transfer functions, the outputs of which are summed to give the output for our process, then we would write the transfer function relating the output to the input this way. Putting these two terms over a common denominator, algebraically, we can also show that this is a second-order transfer function with a first-order polynomial in the numerator. This will have exactly the same dynamics as the second-order system that we just looked at, where we had two first-order processes that were coupled in series. And again, this system will exhibit overshoot if the numerator time constant is greater than both of the denominator time constants.